Hello and good afternoon, everyone. Thank you for joining us today. Today's webinar is brought to you by Waters, the science of what's possible. My name is Tom Serrard, and I am happy to introduce today's webinar and provide a few helpful details before the webinar begins. I am currently a member of the Waters Chemistry Technical Service Team located in Milford, Massachusetts. This edition of our Meet the Experts series is the second part of a three-part series focusing on mass spectrometry fundamentals. Part 2 today will compare the most commonly used MS analyzers and detectors. First, I would like to provide a few friendly reminders before we begin today's presentation. We will have a live text chat during today's webinar. Karen Faherty, Separations and Mass Spectrometry Field Marketing Manager for Waters Corporation, will be handling text chat today to answer your questions. We encourage you to submit questions via text chat during this presentation. Some of your questions will be discussed live at the end of today's webinar as time permits. Questions which cannot be answered today will be addressed, and someone will email you with a response shortly after today's session. Following today's webinar, we will be providing the following to you via email: a link to the recorded version of this webinar, PDF copies of today's slides, and additional related reference materials. In addition, details for our upcoming and previously recorded Meet the Experts webinars can be seen at www.waters.com/meettheexperts. I am happy to introduce today's webinar, which has been prepared by Don Laudicina. Don is presently a Senior Principal Field Applications Specialist at Waters Corporation. He received a Bachelor of Science in Chemistry from the University of Michigan and a Master's degree in Chemistry from Wayne State University. He has nearly 30 years of combined experience working within both the pharmaceutical and instrument manufacturing industries. Don enjoys visiting customers to share his experiences with and instruction on Waters' Quadrupole and time-of-flight-based mass spectrometry systems to solve real-world problems. Prior to joining Waters, Don held the position of Associate Director, Biological Research within Allergan Incorporated in Irvine, California. So with that, let's begin today's presentation.
Welcome, everyone, and thank you so much for joining us for the second of 3 educational installments on the fundamentals of mass spectrometry. I'm Don Laudicina, your instructor for today. In today's session, we'll be examining and focusing on mass analyzers and detectors. The goal of this webinar is to provide some background information on mass spectrometry, discuss how species are analyzed in the MS system, and then look at the most common detectors used today. We'll then look at the type of experiments that can be done by those mass analyzers and how they compare in terms of mass accuracy and speed of analysis. We'll also look at how ions are detected in many modern MS systems. Now, what is mass spectrometry exactly? Mass spectrometry is essentially a technique for weighing molecules. Obviously, we cannot do this with a conventional balance or scale. So instead, we use an analytical technique that ionizes chemical species and sorts them by their mass to charge ratio, or M/Z for short. This mass to charge ratio data is then shown as a mass spectrum. Mass spectrometry is a very flexible and versatile technique that can be used for different analytical challenges across many different industries and application areas. When deciding whether to employ mass spectrometry as part of your analytical toolkit, it's important to be aware of the regulations in individual industries, as the analytical techniques or methods required may be stated within the regulations. Today, mass spec is a very important analytical tool to support both quantitative as well as qualitative analyses. It can be used to confirm expected compounds or perhaps identify unknown compounds in many different types of samples. It can be employed in synthesis to check what is put into a reaction or how that reaction is proceeding, or even to help purify and characterize the resulting material. In the pharmaceutical industry, it can also be used to look at the life cycle of a drug in test subjects to ensure its safety. Mass spectrometry can definitely be considered an information-rich detection method, and there are many advantages of adding it to an existing method or assay. For example, mass detection can be coupled with other detectors, allowing users to gain more information from the same sample in the same injection. Mass spectrometry is highly sensitive, having better or lower detection limits than many other detection techniques. This in turn allows very low abundant species to be detected and analyzed. It is highly selective. Different mass analyzers allow users to acquire or extract information on individual compounds from complex mixtures. Finally, MS can be used to measure any compound that ionizes. This allows the detection of species with no chromophore or low UV responses. Now, let's speak about the components comprising or common to any mass spec system. Mass spectrometry systems can be broken into several parts. First, a sample introduction mechanism. Second, the mass spectrometer itself. And third, the data system, which acquires the data from the mass spec, processes it, and generates results. The mass spectrometer, in turn, consists of the ion source, where the analyte is converted into gas phase ions, the mass analyzer, where ions are separated by their mass-to-charge ratio, and lastly, the detector, where the different mass-to-charge ratio ions are detected individually. Now, we covered the ion source in the first installment webinar, so now we'll turn our attention to the mass analyzer. To detect ions in a useful way, we need a method to separate them. This occurs in the mass analyzer. Once separated, we detect our ions and determine their mass-to-charge ratio based on that measurement. There are a number of commercially available mass spec systems, but the most common types seen in laboratories are quadrupole-based systems, that is either single or tandem quadrupole, time-of-flight-based systems, ion trap-based systems, and hybrid systems, which use some combination of these mass analyzers. There are, of course, other types of mass analyzers not mentioned here, such as sector MS, but these are usually very specialized. We will be focusing today on the most common analyzers, but of course you can find additional information on others online if you are interested. We'll start now with quadrupole-based analyzers. A quadrupole is an assembly of 4 parallel rods arranged equidistantly from a central axis. Through the application of RF and DC voltages, ions can be filtered along the central axis and their mass measured to yield a mass spectrum. Depending upon the exact potential applied to the quad, ions with masses too large or too small will not pass through the quadrupole. These ions will strike the rods and be lost. Ions that are generated in the source pass through the transfer ion optics, which focuses the ion beam, and enter the quadrupole. The ion beam is likely to be a mixture of chemical species with different mass-to-charge ratios. In the example shown here, we have 3 ions at mass-to-charges 220, 310, and 400. A combination of RF and DC voltages are applied to the quad to create a fluctuating field, which will in turn allow for only one specific mass-to-charge ratio to pass. All other ions with different mass-to-charge ratios will strike the quad, become discharged, and the vacuum system will pump them away to waste. In this example here, the voltages are set so that the green ion at m/z 310 is transmitted, and the purple and red ions at m/z 220 and 400 are removed and pumped away to waste. By adjusting the RF and DC voltages, the mass spectrometers can program the quadrupole to pass the mass of interest, or perhaps scan the whole mass range. Now, for single quadrupole systems, mass data can be collected in either of 2 modes: full scan mode or a static mode called single ion recording. Full scan mode is analogous to a photodiode array spectra, where the mass range unit is mass to charge. Individual mass to charge spectra can then be extracted from the scan data if required. Static mode, in contrast, is analogous to a single UV channel. The static mode produces a single ion recording where a single mass to charge channel is selected and all other ions are barred from passing through the quadrupole. Now, tandem quadrupole MS systems have a collision cell in place between 2 quadrupoles. This allows fragmentation experiments to occur. These are known as MS-MS experiments. These can include fragmenting a precursor molecule to look at the resulting product, monitoring a specific product to find its precursor, looking at the effect of a loss of a neutral portion of the molecule, or lastly, looking at a specific precursor to product combination known commonly as an MRM transition. Here is a schematic of the single quad instrument operating in full scan mode. Here the RF and DC voltages are scanning, transmitting ions in sequence. Once the instrument has passed through the entire sequence, it then repeats. This can acquire a scan in milliseconds and is ideal for screening or scouting methods. Here is example data collected from a single quadrupole being operated in full scan mode, looking at extracts, isoflavones, coming from a dietary supplement. This data was collected using electrospray positive mode. If we look at a stacked plot of a UV spectrum stacked above a total ion chromatogram collected in the electrospray ionization mode, one thing we observe is the difference in intensities of the various peaks. In the TIC trace, there appear to be many more peaks. This is due simply to the higher sensitivity of the MS detector relative to the UV. In addition, some of the larger peaks are in different ratios. That is because chemical species can have very different ionization efficiencies. Relative response of analytes also varies within each technique. The y-axis equals counts in the MS trace and absorbance units in the UV trace. In single ion recording, or SIR mode, the instrument is running with the DC and RF voltages fixed, allowing a single mass to be transmitted to the detector. In this example, only an m/z of 220 is being transmitted. Fixing the mass is an excellent way to optimize the sensitivity for a specific species. Each SIR represents a single mass-to-charge ion ratio. It can be collected over the entire time, or it can be collected for a portion of the run. In addition, channels can overlap or be staggered, as shown in the chromatograms here. By aligning two quadrupoles separated by a collision cell, a user can run the same scanning and SIR experiments that were run on a single quad system, but also, more importantly, run a number of more selective MS-MS experiments. These tandem quad systems are the industry standard for quantification, typically using the MRM experiment mentioned prior. We will go into more detail on these experiments in a few slides. However, it should be noted that most vendors use the term triple quadrupole because their collision cells are actually made of a quadrupole. Others, more modern designs, use a different device to fragment masses of interest. So technically they are not triple quads. We will refer to those as tandem quadrupoles. Here is a list of the experiments that can be run on most modern tandem quadrupole systems in MS and MS-MS mode. Since we have already seen how the MS scans work, we will now look at the MS-MS experiments. Product ion analysis involves fragmenting a known precursor ion and scanning a range of product ion masses in MS2, or the second quadrupole. This is the traditional MS-MS experiment. The DC and RF voltage on the first quadrupole, or MS1, is static, passing a selected M over Z into the collision cell. A voltage is applied in the collision cell to accelerate the ion into the collision gas, typically argon. This process results in ion fragmentation. The ions from the fragmentation then pass into the second quadrupole, or MS2, which is then scanned to produce a mass spectrum based on the mass range settings for MS2. A product ion analysis is selective because the product ions in the spectrum can only originate from fragmentation of a specified precursor ion. This mode of scanning is used to gain structural information or perhaps to identify product ions for use in creating MRM transitions. Precursor ion analysis, or parent scanning, is used to determine which precursor masses have a similar fragment ion. MS1 is scanned to pass a wide range of ions to the collision cell for fragmentation. MS2 isolates a specific fragment ion from the fragmentation. Precursor ions pass through MS1 that produce a product ion at a specified mass on fragmentation in the collision cell register a response at the detector. The mass of the precursor ion is then shown in the mass spectrum. Precursor ion analysis is selective because only precursor ions that produce the specified product ion are going to be observed. This type of scanning is used to confirm structural information produced by product ion analysis, as well as screening for groups of compounds with common structural features. Now, neutral loss analysis, shown here, is useful in determining which compounds have a similar fragmentation pattern. Most MS detectors require species to be charged in order to be detected. So if an uncharged fragment of a molecule hits the detector, it will not be observed. However, we can look for the result of the neutral loss by operating both quadrupoles in scanning mode with a mass offset between the two. The offset will be the neutral loss we are looking for. Last but certainly not least, multiple reaction monitoring is a non-scanning mode used for high sensitivity analysis of target analytes and is the primary method of data recording used by tandem quad mass spectrometers for quantitative analysis. In the experiment shown here, both quadrupoles only allow transmission of the specific precursor ion that provides the specific product ion for monitoring. MRM is the most selective and sensitive mode because only a specific ion which fragments to produce a specific fragment ion is monitored for the entire data acquisition time cycle rather than a portion of the cycle in the case of a full scan. An individual MRM does not provide information about other ions in the sample as would scanning over a wider mass range. But as was seen for SIR experiments, multiple MRM experiments can be run either consecutively or concurrently to look for multiple species in a sample if required. Here is a summary table of the different MS experiments that we have talked about that can be run on a quadrupole-based system. Now, let's turn our attention to time-of-flight mass analyzers. Here is a diagram of how time-of-flight mass spectrometers work in principle. Think of it like the 100 meters track race at the Olympics. When the gun goes off, the clock is started and the three molecules, lightest in red to heaviest in blue, start from the same place and are given the same amount of energy by a voltage pulse applied to the pusher. They then separate as a function of their mass to charge, meaning that the lightest species in red arrives at the detector first, followed by the green and then the blue. As they hit the detector, their time of flight is recorded. That time of flight is proportional to the ion's mass to charge ratio. The mass to charge ratio is calculated by the data system and used to generate the observed mass spectrum. In this ideal example, all of the ions of the same mass to charge would arrive at the same time. This would mean all of our spectra would have very narrow mass to charge spectral peaks. In MS terminology, this would give our mass spectrometer incredibly high resolution, something that is always of interest to the mass spectrometrists. But what exactly do we mean by resolution in mass spectrometry? Time of flight MS is one of the MS techniques considered to have high resolution. The black spectral peak shows melatonin at a resolution of 1000, which is the level of mass resolution routinely observed on a quadrupole-based MS instrument. The red spectrum shows the same melatonin with a mass resolution of 10,000, a resolution that is easily achieved by modern time-of-flight systems. With the high resolution, analysts are able to observe all of the isotope peaks of melatonin. The most common MS data acquisition mode for TOF is full-scan MS, where the entire mass range of interest is acquired throughout the LC experiment. From that full-scan data, masses of interest can be extracted during data analysis to form extracted ion chromatograms, or XICs for short. Hybrid MS systems using time of flight, such as QTOFs, are also capable of MS-MS analyses. This type of experiment isolates a species of interest, or precursor, within the mass spectrometer, and it is then fragmented. The product ions from this fragmentation process are then recorded in the MS spectra on the data system. Some modern TOF systems are capable of running an MRM-like experiment, allowing for both high resolution, high mass accuracy data, and quantification to be run on the same system if necessary. Many TOF-MS systems also have other modes of data acquisition that are used for specific applications, where both MS and MS-MS data can be acquired in the same LC run. These methods can be separated into two groups, DDA and DIA. Data-dependent analysis, or DDA, begin in MS mode, and when certain criteria are met, such as specific masses, charge states, or intensities, the MS switches to MS-MS mode, and the product ions are recorded until another set of criteria are met. At that point, the system then switches back to MS mode and looks for other ions to meet the criteria. Data-independent analysis, or DIA, collects data on precursors and products throughout the LC-MS run, typically by altering between MS and MS-MS-like modes. The data system then uses algorithms to assign product ions to the correct precursor ions. In time-of-flight MS, the TOF system cannot physically filter individual ions, so the TOF system records all of the ions at the detector, so some of the experiments run on a quad-based MS system are not available on a TOF system. These include neutral loss, or MRM. But some modern TOF systems are capable of running an MRM-like experiment by only recording masses of interest and discarding the other masses, allowing for both high-resolution, high-mass accuracy data and quantification to be run on the same system if necessary. The third mass analyzer regularly seen in the MS lab is the ion trap-based mass spectrometer. The Quadrupole Ion Trap mass analyzer was developed by the Nobel Prize-winning mass spectrometry pioneer Wolfgang Paul. His work in the early 1950s led to the development of the basic parameters of today's common benchtop instruments. A schematic of a quadrupole ion trap mass analyzer is shown here. The ions enter into the trap through the inlet and are trapped through action of the three hyperbolic electrodes, the ring electrode, and the entrance and exit end cap electrodes. Various voltages are applied to these electrodes, which results in the formation of a cavity in which the ions are trapped. The ring electrode RF potential, an AC potential of constant frequency but variable amplitude, produces a 3D field within the ion trap. This traps the ions in a stable oscillating trajectory. The exact motion of the ions is dependent on the voltages applied and their individual mass-to-charge ratios. The stable trapping of ions is shown in the left-hand side of the figure. A trapping RF amplitude is typically applied for between 0 and 30 milliseconds, during which time ions formed from the sample molecules are stored. For detection of the ions, the potentials are altered to destabilize the ions, resulting in their ejection through the exit end cap. The ions are usually ejected in order of increasing M/Z, or mass-to-charge ratio, by a gradual change in the potentials. This stream of ions is then focused onto the detector of the instrument to produce the mass spectrum. This is shown on the right-hand side of the figure. Ion trap-based systems can perform full scan and product ion scans as the other MS systems we have described can do. But the very nature of trapping and ejection makes a quadrupolar ion trap especially suited to performing sequential mass spectrometry, or MS to the N, experiments for structural-based studies. It is possible to selectively isolate a particular M over Z in the trap by ejecting all of the other ions from the trap. Fragmentation of this isolated precursor ion can then be induced through collisional-induced dissociation, or CID. The isolation and fragmentation steps in the ion trap can then be repeated a number of times and is only limited by the trapping efficiency of the instrument itself. Nobel laureate Paul also developed the linear ion trap, which functions in a similar fashion to the quadrupole ion trap. Instead of using circular donut-shaped electrodes, the linear ion trap electrodes are similar to those of a quadrupole described earlier. The Orbitrap is a trap consisting of an outer barrel-like electrode and an inner spindle-like electrode that traps ions in an orbital motion around the spindle. The current from the trapped ions is detected and converted to a mass spectrum by processing the data using the Fourier transform of the frequency signal. Both of these types of ion traps are seen regularly in the modern mass spectrometry lab. Many modern MS systems use more than one type of mass analyzer to expand the range of experiments that can be run on it. Examples of this include the QTOF mentioned earlier. The QTOF, shown on the left, uses a quadrupole, a collision cell, and a TOF mass analyzer in series, which allows for both high-resolution MS and MS-MS experiments to be run on the same system. This type of hybrid system was pioneered by Micromass in Manchester, England. Micromass is now part of Waters. Another example shown on the right is a quadrupole ion trap system, where the system uses a quadrupole in combination with an Orbitrap. Now that we have looked at the common types of mass analyzers found in most modern MS labs, let's turn our attention to how ions are detected in these mass spectrometers. As we mentioned earlier, an MS system can be broken into several parts. On the left, we see the sample introduction mechanism, followed by the mass spectrometer itself, and lastly, the data system, which acquires the data from the mass spectrometer, processes it, and generates results. Now, the mass spectrometer itself consists of the ion source, where the analyte is converted into the gas phase ions, the mass analyzer, which we've just discussed, where the ions are separated by their mass-to-charge ratio, and now the detector, where the different mass-to-charge ratio ions are detected individually. Once we have separated or isolated our ions of interest based on their M over Z or mass-to-charge ratio, we need a method to detect them. There are two common detector types used in mass spectrometry. These are the electron multiplier and the photomultiplier-based detector. We will look at both of these in turn. Let's start with the electron multiplier detector. In an electron multiplier detector, the ions from the mass analyzer strike the anode surface and electrons are ejected from the surface. These electrons, in turn, hit a dynode and cause an electron cascade, since there are more dynode surfaces down the detector. Each electron that hits a dynode produces several electrons from that surface. These multiplications produce a current, which is detected at the cathode, and an ion strike is magnified by up to 1 million times. It is this current which is translated into the signal seen in the mass spectrum. Electron multipliers are the most common detector in MS systems. They are very sensitive and have a fast response, but in many systems they need to be replaced every few years. The second common detector found in many MS instruments is the Photomultiplier Detector. In the Photomultiplier Detector system, or PMT, the electrons created from the conversion dynode strike a phosphor screen. The excited phosphor emits photons. The photons strike a photocathode at the front of the photomultiplier to produce electrons, and the signal is amplified by the multiplier. The data system then receives the signal. Keeping the photomultiplier permanently under vacuum prevents contamination and allows the detector to maintain its performance for a considerably longer period than conventional electron multipliers. This detector is used in nearly all Waters quadrupole-based MS systems. Now that we've described the three most common types of mass analyzers found in many labs, the quadrupole-based system, the time-of-flight-based system, and the ion trap-based system, let's compare these three so that we can gain a better understanding of each. Let's begin by comparing mass accuracy. Mass accuracy is a common measure of the performance of a mass spectrometer, particularly in high-resolution systems, as we've described earlier. Current time-of-flight systems typically quote mass accuracy in relative terms as parts per million, or ppm. And they generate data with mass accuracy in the low part per million range, even when using fast chromatography. As a comparison, quadrupole and ion trap systems typically quote mass accuracy in absolute terms. They have a mass accuracy of about plus or minus 0.1 Dalton. However, it should be noted, the mass accuracy of an ion trap system can depend on the model and other factors such as the scan speed and the mass range of that ion trap system. Shown here on this slide is information gathered from a quadrupole MS instrument. With a quadrupole MS instrument, 1 decimal place is typically used when measuring masses. With this nominal mass measurement, there are 37 different possible formulas based on elements carbon, hydrogen, nitrogen, oxygen, and sulfur that are within a 50 part per million mass tolerance window. This makes it very difficult to confirm a known species, and even more difficult to identify an unknown species from that data alone. Modern quadrupole MS systems are capable of running both MS and MS-MS experiments during the same run, so we may be able to obtain more information from this type of scan. However, the mass accuracy would not be improved. In contrast with our last slide, here we show a mass spectrum collected off of a time-of-flight mass spectrometer. Now, as we discussed earlier, time-of-flight systems are high-resolution instruments. They are capable of accurately measuring mass-to-charge ratios to 4 decimal places. This allows us to lower mass measurement errors to within 3 parts per million. As a result, this makes it easier to confirm known species within a very tight mass tolerance window. In this example, the accuracy of the mass measurement allowed us to tighten the mass tolerance from 50 ppm to only 3. After doing this, we see that the number of possible formulas for this species drops from 37, shown on our last slide, to only 3 when considering the exact same elements as we did on the previous slide. If we know sulfadimethoxine, for example, is in our sample, we could use this information to confirm its presence in the sample since we know its formula and have at the top of our list of possible formulas a hit matching its protonated molecular formula. Now, if we were working with an unknown compound, we would feel very comfortable saying that the peak is consistent with an elemental composition of C12H15 N4O4S. But to know how these elements are connected within the molecule, we would need to perform other experiments, such as an MS-MS acquisition, to obtain even more information. The ability to quickly acquire high-quality mass spectral data is an important factor to consider and will be related to the type and speed of the chromatography system being coupled to it. Time-of-flight systems record all of the mass range being acquired all of the time. This can give these systems an advantage over systems which have to scan the mass range. For example, quad-based systems must change voltages as they scan the mass range, which can slow acquisition rates for full-scan MS. Acquiring faster or a wider mass range can lower the time spent on each individual mass, meaning lower quality data could be acquired. Total cycle times for ion trap systems are comprised of multifunctional stages and can vary significantly based on desired mass analysis times and selected mass ranges. In summary, the type of experiment you wish to run may affect the type of instrument you choose. If you wish to have a high mass accuracy and resolution, you may select a TOF system. If you are running quantitative experiments, a quadrupole-based system would give you the widest linear response as a function of concentration, allowing you to quantify your required range. If you needed to run multiple rounds of MS-MS experiments, perhaps, the ion trap would provide you that option. And of course, you may not have access to all the instruments you would like, and that may be the limiting factor. So, in conclusion, there are a number of common mass analyzers available today, which will provide a wealth of knowledge about your sample. The type of data you need will, of course, influence your choice of mass analyzer, and the detector in your MS system will be critical to the recording of your data. We thank you for joining us for Part 2, Mass Analyzers and Detectors. In the next module, we will be discussing some advanced topics in mass spectrometry such as ion mobility and mass spec imaging. We hope you can join us.